Okay, hello everyone. Welcome to today's sustainability seminar. I am Beth Mashesky, Senior Scientific Specialist at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. A couple housekeeping items before we get started. I'll remind our audience members here in our conference room to please silence electronic devices as we are recording today's webinar. We will be holding all questions until the end. At that time, for everyone in our conference room, I'll bring the microphone to you so that everyone online can hear your questions. For those online, you'll remain muted for the entire webinar, but you can type in your questions through the GoToWebinar toolbar at any time, and I will ask those at the end. So with that, I'm very pleased to welcome today's speaker, Jennifer Field. Jennifer is a professor in the Department of Environmental and Molecular Toxicology at Oregon State University. She earned her PhD in chemistry from Colorado School of Mines and was a postdoctoral fellow at the Swiss Federal Institute of Aquatic Science and Technology in Dubendorf, Switzerland. Her research group generally focuses on understanding the fate, occurrence, transformation of emerging contaminants in natural and engineered systems. Her group conducts laboratory and field studies to quantify the behavior of PFAS at military sites impacted by repeated historical applications of AFFF. Her group also creates analytical methodology aimed at closing the mass balance of PFAS at those sites to inform and assess remediation efforts. Jennifer is considered a pioneer in the area of PFAS after having studied them for 20 years. So Jennifer, thank you for joining us, and the webinar is yours.
Well, thank you very much. And I don't know if you mentioned, but I'm an Illinois native and grew up near Abingdon, Illinois, and have been in Oregon for the last 20 some odd years. So I still have family in the region. And so thank you again for the invitation. Let's just get started. And the title here hopefully gives you an idea of the content. We want to talk about some of these newly discovered compounds. News kind of relative term. Work goes back all the way to 2010. But of course, I've got partners in this discovery, and this is Krista Barzan-Hansen, who's now with Elmira College up in New York. And of course, Chris Higgins, Simon Roberts, and there's actually a number of people who have since contributed to this understanding. Ben Place, Will Bakke, and Alex Robel now, Radoa. And so for those of you who might be aware of PFOS and PFOA, there's been a whole lot of focus on that. And one of the first questions that I have in the presentation, if I can get it to go forward, which is more challenging than I thought. Here we go, is with that focus on PFOS and PFOA, is this still just the focus? In a lot of areas it is, but what I want to do in this presentation is try to explain why it's important to go beyond just thinking and working on PFOA and PFOS. And so here's some examples of maps. In the left-hand corner, left-hand side is a Michigan map from Michigan. It's a former military base. You can actually see the flight line and kind of like the ghosty lines pointing up into the upper right. You can see all these highly colored plumes of a variety of PFASs, per and polyfluoroalkyl substances, hitting freshwater lakes, rivers, and ultimately Lake Huron. In fact, this river shown in this map is the Saukla River. It's one of the few that has a no-eat fish rule. And on the right-hand side, you see a weird-shaped plume. That's actually coming from Australia. That deformation and that sort of non-traditional plume, you know, for those of you who work in groundwater, the plumes on the left look kind of like maybe what you'd expect. The one on the right, that blob, looks a little bit weird. That's partly because, of course, Australia's been in the news recently, is they brought up a lot of subsurface water and used it for irrigation. And then you have a very lateral spread of the contamination. And so when we look at these maps, we typically are plotting or see plots of PFOS and PFOA, but as the question asks, is that what it's all about? So in our lab, since about 2010, because of CERTIP funding, we've actually focused on reverse engineering AFFFs. And AFFF is an aqueous film-forming foam, and this is the material that's been used to put out fires, hydrocarbon-based fuel fires, since the 60s. And the Navy requisitioned or requested that 3M create a formulation, and they did back in the 60s. And so what we have is data here shown graphically about what is in that bucket of light water. And we have different dates of manufacture and different lot numbers, et cetera. But what we know, going back to about 1980 or so from various formulations, is if we look at that pie chart with colors, the lion's share of the highly fluorinated substances are in fact the sulfonate family. So here the shorthand is PFASs, so persulfonic acids, and of that PFOS is the dominant sulfonate. But then you get into some of these other colored bands. You get the carboxylates. So sometimes people talk about PFOA-based AFFF. Well, I've actually never seen an AFFF that's, quote, based on PFOA. It's a minor component in the 3M AFFFs we've looked at. When you start to see carboxylates showing up at or equal to PFOS, we're possibly looking at more older formulations, or those carboxylates might actually be transformation products of some of those active ingredients in the telomere formulations. And then the other little pie slices here are other anionics, other zwitterionics, other cationics. And you can see there is mass there that is made up by other functional groups. So we have, negative charge, positive charge, and a zwitterion is a chemical that has both. An example is actually the chemical in the lower right-hand corner. I actually drew, there's an error on this structure. It should be, this is a sulfonamide. You've got that cation out there on the end, but that nitrogen with the hydrogen should actually be deprotonated. And that's because the functional group there, the highly fluorinated tail and the sulfur with the 2 oxygen atoms, is really electron withdrawing. So this is actually a zwitterion in here, and that's an example of what's actually in the AFFF itself. All of these molecules are going to contribute to the total fluorine, and there are total fluorine methods out there. We'll touch on that here coming up. And so the precursor fraction in here, which is running about 10%, and we've just tangled with an AFFF recently where some of the other compounds are up to 30%. So got to take this as an example. These other molecules, the ones shown on this page with the positive charge groups, all those R groups with atoms, sulfur, oxygen, carbon, hydrogen, nitrogen, those are all oxidizable and potentially caught in the total oxidizable precursor assay as well as in total fluorine. And so this is an interesting fraction because the properties deviate significantly from what we attribute to the carboxylates, PFOA, and the sulfonates, such as PFOS. Because these materials are potentially sorbed because of their strong cation exchange, and that R group has some biodegradation potential. Then if we switch our attention to the other products that were used out there, going all the way back to the 70s. So these were qualified on the mil spec for military use. And so even though if you take a look at these molecules, they might not be ones you would recognize. These are the active ingredients in the Ansel formulation. Ansel would be the one down here in the center. The telomer, it's a telomer thioamidosulfonate, and the acronyms get kind of crazy here. And these upper two molecules are actually the active ingredients in National Foam. And actually, these are the molecules that are in the AFFFs that are used in the current mil spec today. So if you went out and bought a bucket of AFFF on the mil spec, you're going to potentially tangle with these molecules. And as you might recognize, they're not actually captured by analytical methods that have lists of compounds that we know, like the carboxylates and sulfonates. What is interesting, though, is all the molecules shown on this page. If you look at the blue box in the lower right, you can actually see what we call the telomere sulfonate. That is on lists that commercial labs are running now. That's the telomere sulfonate. And what's curious to know or to notice about these molecules compared to PFAS, where the sulfur is attached directly to the fluorinated carbon, in this case, they're not. And that was a very deliberate way to get around patents. So if you look at the 2 non-fluorinated carbons that are attached to the fluorinated carbon chain, that's the tell or the characteristic of the molecule that's saying these are coming from telomere-based chemistry. And so whenever we see 2 non-fluorinated carbons after the fluorinated tail, you're like, yep, that's coming from telomere chemistry. So the telomere sulfonate down here, to the best of our knowledge, was never an active ingredient in the AFFF. It wasn't there in large concentrations. And what I mean by large, I mean grams per liter. In a bucket of concentrate, the concentrations are in grams per liter. That's percent or parts per 100. And so when you think about the EPA's health advisory level of 70 nanograms per liter, you have to dilute a typical AFFF 1 billion times to bring that concentration down to the EPA health. That's B with a billion. And so that's part of the problem about what we're up against. But the telomere sulfonates here, in this case, we see them in groundwater. We don't see them that much. They're only minor components in AFFF. It's an indicator of the biotransformation of the telomere-based active ingredients. So if you have sites where you're picking up telomere sulfonates, that is an indication that telomere-based AFFFs have been used. And if you see PFAS, you're like, oh yeah, it's also 3M. We often see AFFFs commingled at various sites because simply they were for sale in the same periods of time, and mil-spec had baked into its criteria the interchangeability of these materials. So they were designed, one bucket goes in a fire truck today, a separate formulation goes in tomorrow, that the mil-spec had the ability, that's part of the qualification process, that they could mix and still be effective. So when we look at the telomers on this green, what we know, and what's increasing now in the literature, some great stuff out by Scott Mayberry's group up in Canada, and also by Lisa Alvarez-Cohen down in Berkeley, is that these molecules are partially biodegradable, and they indeed form telomere sulfonates, and they form carboxylates. But something to notice about these molecules, unlike 3M, 3M's chemistry was a bit messy. It is branched linear, they've got cyclic components. Here, telomere chemistry is linear. So the carboxylates and the telomere sulfonate that result from the biodegradation of these compounds are only linear. So if you have sites and you're dealing with this issue, and you can get, because contract labs are either in your own lab, or if you're buying analyses, they can begin to break down the branched and linear. A linear only carboxylate or a shift toward linear tells you that you have the potential for telomere-like compounds in your site. But again, none of the methods we have now in the commercial domain are picking up these active ingredients. There might be one exception. This molecule, the second one down, I think is now part of the Wellington standards. And the sulfur atom does oxidize in situ, and you can see transformation or partial transformation products, and these are all oxidizable, which means if you have a site where this was the dominant, you can't see the original active ingredients by any commercial lab techniques, but that's where alternative methods like total oxidizable precursor assay and total fluorine come in handy. So here's an example of what's known in the literature about the breakdown of the ancel parent product. So this is a thioamido sulfonate. You see the sulfonate on the end, anionic, think it's mobile in the subsurface. This reduced sulfur atom, this thioether bond is labile, and it picks up 1-2 oxygens in the subsurface, and that's the beginning of this pathway toward telomere sulfonates, which you see circled in blue. And that's the actual under anaerobic or low oxygen conditions of a lot of AFFF sites, because remember, they tossed on fuels, they tossed on AFFF, which have high BOD, COD. These systems really went anaerobic. And telomere sulfonates are not anaerobically biodegradable, but they are under anaerobic conditions. So when you have anaerobic systems pop out, let's say, and hit surface waters, these materials, you might see them decline and actually go toward the molecules showed on the lower half of this transformation pathway. And that's the saturated and unsaturated carboxylates, and then ultimately these linear only carboxylates. And so we do know a little bit about the transformation. So here's what the method is typically tossed around as being available on the commercial market. And the method world is evolving quickly. There's ASTM methods, EPA is coming out with methods, but this is where we started. And this is what it was, a drinking water only method. And of course, it is implied to drinking water still to this day. But as we move to groundwater, sediment, and soil, this method, you actually see modifications and other methods coming up. But it requires solid phase extraction, and it was for a limited number of compounds. It was 9 carboxylates, PFCAs for shorthand, 3 sulfonates, PFSAs, and 2 sulfonamido acetic acids. And the UCMR program, which your region may have participated in, they only look for 6 of these things. And so it's a pretty limited palette, but it is a US EPA method. And I don't know if there's any analytical chemists online. There's usually not that many. It's kind of a small audience. The SPE, solid phase extraction, is the method that method 537 relies upon. What's made SPE challenging in some cases is the really short chains really move through this media, and they're more difficult to capture, which is why methods have evolved since this time. And so SPE is commonly in practice. I'm not a fan of it. We've found ways to get around that, but it's certainly a practice that's out there. And so our approach is a small liquid-liquid extraction. because our goal is to go for a very broad palette. I don't show all the compounds we're looking at, but we're up to now around 400 discrete PFASs that we can find. They're not all equally abundant and equally valuable, but we've amassed this library that we now call our suspects. And so by doing a small liquid-liquid extraction and doing a very large volume injection and putting it through an ion exchange type chromatography, we're able to get from very low to very high with a whole host of head groups, from cationic to anionic to molecules having both charges. And so when we first started applying our new expanded methodology, you could start to see, you know, like what is normal for groundwater? And I think the first thing to notice is the PFOS numbers here. We're in micrograms per liter. So this is a site where it is a milligram per liter. That's pretty high. And again, several orders of magnitude greater than the EPA's health advisory level. And that's pretty typical for an AFFF source zone. And at this time, you know, PFBS, PFBA, the short chain analogs of PFOS and PFOA, they exceeded the Minnesota health risk limit. We now have states implementing different limits for different compounds. The feds still just focus on PFAS and PFOA. And we see in these upper two, we see the thiamethosulfonate, that first entry on the first line. That's the active ingredient in Ansel. And then you can see down below it, the fluorotelomere sulfonate, the 6-2 FTSA, really is greater than the parent compound. Again, that's that biotransformation that occurred after application, probably when there was some oxygen around. And it's not uncommon to see this PFHXS. This is a C6 analog of PFAS at fairly high concentrations, and in case site 2, it's even higher than PFAS itself. And so these precursors that are up in the upper, you know, couple lines of this graph, these are the molecules that we're talking about. You can see in some cases that the amount of mass concentration is not really trivial. And AFFF source zones are some of the hottest sites that we've ever seen. Our prize winner to date is PFOS at a milligram per liter, 1,000 micrograms per liter. We've seen PFOA at 6.6 milligrams per liter, and that telomere sulfonate is my all-time winner at 14.6 milligram per liter, or 14,600 micrograms per liter in groundwater. This is very near source zones, which is why source zones are potentially informing some of the hits in the drinking water in watersheds. And so precursors really came up in the last few years, really people talking about it. What is this other stuff? And of course, it's a contextual word. Precursors are often referred to as those molecules that can biodegrade, biotransform, also biologically as also abiotically, say through oxidation, to these persistent dead-end perfluoroalkyl carboxylates and sulfonates. And again, only 2 of those have an EPA health advisory reaction. And so this is a whole host of what we think of as parent molecules or active ingredients in AFFF, and they give rise to these metastable type intermediates. The problem is we don't really have methods for them. And so we've got quite a few detections now, and this is really going up all over the world, both in Canada, a lot of good work there, in France, in China, a lot of focus on these precursors. And so it goes well beyond the molecules captured by method 537. The reason precursors are important is if you're looking at a contaminated site, you really want to have an idea of what's there. So having the ability to get at precursors is important for site characterization and for the development of conceptual models. Also, if you're trying to understand what may be mobile, some of those precursors like a C6 sulfonamide, the FOSA, the shorter version of FOSA, that's actually around, and that's a pretty mobile molecule. We see that now in surface waters. And understanding what's there with tools and technology that exists today may also help minimize impacts as well as future liabilities. Because the question is, what did you know when? When did you know precursors are around? Well, we know about that, and we have known about that now for a couple of years. And then also, if you know precursors are there, you might be very selective about what remedial technologies you select. For example, there's different kinds of approaches, and we'll talk here in a moment about the top assay. But if the top assay is an oxidative and you can create carboxylates, as long as you know what you're creating, you can plan for it. It's when you get into an area and you don't realize precursors are there that you could actually end up increasing your problem and the scope of the problem. And the other reason why precursors are matter is because now, through a lot of efforts, both state and local regulators and the public are becoming increasingly aware of the presence of these precursors. So that's why we talk about how do we close the mass balance? What are the tools out there? And it's because we need something like this because, again, as our understanding and our analytical capabilities go up, the number that we identify has gone up, and they're in a variety of different media. And so having an idea of what's in that source term really can help you be much more prudent about selecting remedial technology. And I guess the bottom line is minimizing that future liability. So what are the tool sets? Well, we have the total oxidizable precursor assay. This was developed by Dave Sedlak and Erica Houts. And what is kind of like the, I guess it's an interesting analog, you know, people think of Post-its, which kind of irony here is a 3M product, as a failed adhesive. It was a very, very successful failed adhesive because it was partially sticky. Well, the top assay, as I understand it, was a early attempts to try to oxidize precursors, and it didn't go well. And Dave and Erica noticed that they keep getting carboxylates. And of course, they turned lemon into lemonade and went, hey, maybe if precursors all oxidize to carboxylates, what we can do is capitalize on this net bump up in carboxylates after oxidation. So what they did is, that's what the top assay is. They oxidized groundwater, aquifer solids, soils, and AFFF. They looked at the composition before and after oxidation, and sure enough, those precursors oxidized to the carboxylates, which we can see with today's technology. So the top assay is a really clever way to get at the totality of precursors in these various media by monitoring and quantifying the net increase in carboxylates. And it turns out, you know, there's some limitations. You have to do the analysis twice. That makes it a little more expensive. I should point out now, it is commercially available. And there's a number of labs that, off the top of my head, I know Vista, Axis, which I think is now part of SGS, and Test America. I believe they all offer, and maybe others are offering the top assay. And so that's the good news. It's accessible. And so if we take a look at what does top assay data look like? So here is pre-oxidation in yellow bars and post-oxidation, or the larger blue bars. This is a single sample. It's an AFFF contaminated groundwater. And what you get is the profile of carboxylates. And of course, there were other molecules in there. But the yellow are the profile of the carboxylates before oxidation. And then the sample was subjected to oxidation. And you see this jump up in C4, which is PFBA, C5, C6 was PFHXA. And then, of course, you actually don't see a statistical increase in the C8. It turns out when you look in groundwater and sediment and soil, it's not uncommon to see the C6 pop up more than the others. And that's actually consistent with what we know about the precursor chain length. The thing about the top assay is it doesn't preserve the original chain lengths of the precursors. You have to know that. It definitely is going to shorten things up. That's why you almost always see pops in 4, 5, 6, and maybe to some degree, and to a lesser extent, 8 or 9. So you don't get a one-to-one correlation. But you can quantify this net increase, and for that reason, it's pretty useful. What you don't see on the commercial market, I think just because of cost purposes, you don't see the triplicates necessary to do the statistics. So for example, that's why we did it in this graph. You can see that the pop-up in 4, 5, and 6 is statistically significant. 7, 8, and 9 are not. And so you have to kind of be a wise consumer of top assay data. Here's another example, a low-level drinking water where our instruments are going to, you know, be down on the lower end. You can see that only the C4 carboxylate gave a statistically significant increase. So you have to be a wise consumer when you are looking at and thinking about top assay data. And Graham Peasley, who's literally just up the road and across the state line from you, is the person who's now at Notre Dame, who I met him, and he was doing bromine in flame retardants in foam. And I said, well, if you can do bromine, can you do fluorine? And he's like, well, I don't know, give it a go. And now we have Piggy, and he is been tremendously successful in looking at and presenting a number of different applications. Great speaker. I would highly encourage you to maybe bring Graham on as a speaker at your seminar series. He's a very engaging speaker. And so he's got a really great gizmo. It's very expensive, not mobile, although they're working on that. And what it is a spectroscopic method that excites the nuclei of fluorine atom. And what you get is signals that are characteristic of the fluorine. And so we've actually done quite a bit of work with Graham, looking at papers and textiles, And he's now even absorbing water onto SPE media, and he's got a crazy fast 3-minute analysis. He doesn't get any interferences, and to some degree non-destructive. And so what the data looks like, and hopefully I can get my slides to advance, is something like this. So he's looking at these signals in the lower right, gets 2 distinct signals for fluorine atom. He's been able to calibrate. He puts his media on these little targets, and he puts it in front of his beam. And I think he's even improved on these numbers since I made these slides, which is now a little bit ago. And so I think he's got his limit of detection in water down below and closer to the EPA health advisory limit. And so we've actually put top assay and total fluorine together when we look at papers and textiles. And right now we're looking at firefighter uniforms. And it really helps put some of the specific precursor measurements into perspective. I really think total top assay and total fluorine are super useful tools. And then we move to LC time of flight, which is the instrumentation we have here in the laboratory. Increasingly popular, hasn't made it quite in the commercial lab. We took advantage of the fact that a LC quadrupole time of flight mass spectrometer is really seeing everything all the time, whereas the other information that's typically gathered is with a triple quad instrument, which is really an instrument that's set up to look for just what you want to look at, whereas this QTOF sees everything all the time. And so then it becomes this giant data mining exercise. And it turns out if you take ions, which is what's depicted on the bottom axis of this graph, the x-axis, and then you actually do a simple transform where you multiply those masses by the nominal mass of the CF2 group, which is 50, divided by its accurate mass, all of a sudden your points start lining up like birds on a wire. And I fondly remember, power lines in the Midwest, and you just see these birds all line up on the wire as you drive down these really flat roads and rolling roads. And so these birds line up. And so what we see is sulfonates. Down here, this PFASs, C8, PFOS is that C8 in the low, that's the second line from the bottom in that graph, and you work your way down, 7, 6, 5, 4. And when we did this, the student brought in, and those 2 black dots weren't black, they were just kind of open circles. And I said, well, what are those? Those are part of that series. And that's actually how we found the C2 and C3 sulfonate, because this data treatment, pretty straightforward data treatment, revealed we've been missing these members of the homologous series for a while. And so in this graph, you can see the carboxylates are identified, telomersulfonates, and then there's these mystery lineups of birds. We don't know what some of those were. And so that became the target of some non-target analysis, trying to figure out what classes have we missed. And that's where this big burst of information starting back in 2010 came from.
What we have on this particular slide is, so I mentioned, where do we get this? We literally fished molecules out of AFFF concentrate, out of AFFF source zone. And so the bars in red, every bar stands for a different class. And so what we found is, here's the molecules that occurred in both AFFF in groundwater. And so you can see the different classes that are present. But here in green now are the ones that are same molecules, they're present in AFFF in groundwater. And you're like, well, that's convenient because that allows us to identify AFFF as the potential source of these molecules. And we had 3M, we had telomers, and both in blue. And the molecules in blue now were in AFFF, but not groundwater. And you say, well, why is that? Well, it could be that these molecules have since been transformed, removed by sorption, because now they have those interesting head groups, or they're simply not, persistent, that because of those processes, they've actually been removed from groundwater. And in yellow, what you see are, these are molecules that existed only in groundwater and not in our AFFF collection. And that suggests that these molecules are actually transformation products, in that they're on the move and are found down gradient of these source zones. And they're also persistent, because the groundwaters in this study, they haven't seen a new AFFF addition for 20 years. And so if you start looking at individual sites to get a sense of how important are these precursors, what you see in the lower bottom right, it's a chromatogram. But I think what, for those of you who aren't analytical chemists, you can almost think of it like a frequency and abundance scale here. We have retention time on the right, on the x-axis. Turns out that's a good model of hydrophobicity. That's well known, that things that have a higher retention time in a analytical system are simply more hydrophobic. That's why you see PFOS plotting out in this blue line out to the right. It turns out that 8-2 telomere sulfonate, it's even farther to the right. And so what you see at, let's say, 10 out of 15 sites, we normally see carboxylates and sulfonates in the blue line. These are the typical ones you can pick up by method 537 in, if you're using a drinking water method. And it's only these little black guys down here at the bottom. You can see at this site, precursors don't seem to be a significant fraction of the mass. About 16% is missing. But if we go to a different site and inspect this chromatogram, we look at the blue traces. Those are the ones caught by method 537 type analyte list, so carboxylate sulfonates. You'll see that we need those newer methods that are coming out to pick up the purple telomere sulfonates. And the black ones still are not captured by any methods out there. So we're missing 20% in our precursors, and you've got to be looking for telomere sulfonates if you want to get that 15% mass. So here we have sites where we have these materials that are not captured by conventional methods. You can also think of these spikes and sulfonates and carboxylates down in this chromatogram as sort of like gates and indicators of hydrophobicity, which is about transport. And so all those black lines are filling in between PFHXS and PFOA. That suggests that those black lines, those classes, have mobility that are somewhere between the C6 sulfonate and PFOA. And so when you start, again, looking at that x-axis is a clue about mobility, and it also may be a clue about bioaccumulation. That actually we'll have to see. And here's another case where it gets even a little bit more crazier. We have quite a bit of, if you were running the method 537 list of analytes, you get about 64% of what's in there. And there's about, and the remainder are in these telomere sulfonates. And on the black, you can see, again, shifting toward lower masses, lower retention times. That's signaling potential mobility in that subsurface. And those are the ones we really want to start paying attention to. When you start looking at the molecules, each molecule also has the potential to tell you something about that site. When you see in the upper right-hand corner, 10 out of 15 sites, we're seeing this sulfonate. This comes from the 3M chemistry. Actually, the top left two do. So we've got mobility in groundwater because they're anions. And again, I should have a negative charge on that first upper left-hand molecule. There's a lot of mobility when you have 1 or 2 negative charges on a molecule. And that C6 sulfonamide, that'd be where N equals 6 in that second molecule in the upper left. That thing is on the move in groundwater and makes it to surface water. We've got molecules that are PFOS-like that are coming out of the AFFF containers. Remember that that chemistry was pretty messy, and there are a lot of other reactive products. This very bottom molecule is actually a transformation product of the ancel chemistry. We actually see that being more abundant than the actual parent itself. And how about that crazy molecule on the right-hand side of your page in the middle? Look at the size of that molecule, but it's very mobile. It's moving, it has a retention time of a molecule about half its size. Why is that? Well, we've got a charged site and we've got 2 anion sites. So high mobility in the subsurface, and we have decent concentrations, and yet we don't really have any toxicity data. So if we switch a little bit here and think about drinking water, what we know is that the WHO paper that came out not that long, 2016, basically showed that if you're here in the United States, you had a 10 to 35% increased risk of having exposure through your drinking water if you lived in a watershed at a military base. And that's because some of these interesting compounds, very diverse compounds, high concentrations, are really focused in areas where there was these repetitive firefighting practices. We now know, of course, that those kinds of fire training practices happen at municipal sites, fire training sites, firehouses, where buckets were washed out. We're seeing well, we know that wastewater treatment plants are point sources. We know landfills are point sources, so we're becoming more and more aware of where you can find this. But this drinking water hit has definitely gotten people's attention, and in Sweden, actually is a really, they discovered it, and they even had PFBS in blood, and PFBS has a half-life in humans under 30 days. That's probably a reflection of steady state daily exposure, and so you can end up with measurable levels of compounds with short half-lives if you've got that steady state exposure. So looking at GAC treatment, there's a lot of this being installed around the country and a lot of interest in it, really trying to help define it. Detlef Knappe, who would also be a great speaker in your seminar series if you haven't had him already. He really specializes and is an expert in GAC treatment. And historically, people are really focused on taking out PFAS and PFOA. But if you look in that upper right, look at all the other stuff that's in that source water that you're trying to treat, and imagine only being focused on PFAS and PFOA. Those are two marks, and they're the most hydrophobic. In other words, those are the easiest ones to get out. It's the short stuff that's very challenging to get out by GAC. And so if you look at the bottom right panel, this is breakthrough data, and I want to say this is either, and I forgive me for not putting the reference on here, this is either Gary Hohenstein of Syria or it is Tim Appleman's data. And you can see the early PFBA breakthrough relative to PFOA and the other compounds. And that PFBA sneaking through is expected because of its short chain. And so if we're setting our GAC turnover or the breaking it down and resetting it to PFOA, which is in the orange line, or PFOS, which is in this blue line, you might make a very different decision if we're gauging your turnover, if you were benchmarking it against, say, PFBA behavior. And of course, this is attached to health limits. And so I think in this case, this water, the PFBA, notice the y-axis is C over C naught. It doesn't tell you concentration. It's just, it's a relative breakthrough. Those values did not exceed state drinking water limit, and that's why they were allowed to operate the system in this manner. But the focus here is how to deal with precursors. They're going to fall in intermediate positions along the line of the carboxylates and sulfonates because they have hydrophobicities that fall in between the ones that we monitor, the carboxylates and the sulfonate. When we think about sorption, my student Krista Barzan-Hansen, who's now up in Elmira, she'd also give a good talk. She looked at the sorption of the 6-2 that's the fluorotelomere sulfonamidobutane, FTSAB. It's a zwitterion, and there was a cation in that mixture as well, this FTSAM in the lower hand corner. And when she did absorption experiments with 5 to 6 different soils, different pHs, first of all, the cations are gone. Nothing to measure. You can't plot an isotherm if there's nothing left in solution. And so that's why there's no gold dots on this plot of adsorbed concentration on the y-axis and the aqueous concentration on the x-axis. And that is feeding into the hypothesis that cationic materials are sitting up strongly sorbed through electrostatic type interactions in source zone sediments. And of course, the question is what are those doing in the long term? Do they biodegrade? Do they ever desorb? And it helps us understand why source zones still exist today because of this strong sorption. And the anions, which are the telomere sulfonates, the 6-2 FTS, A2 FTS, they were the least sorbed of this suite of compounds. And these cations zwitterions are in between. Just exactly, for those of you who speak German, that's that Psi is 2, it has the 2 different charges on the molecule. And what you see is this intermediate behavior. And this kind of information has also been obtained by other researchers in Canada and France, people really trying to take a look at these multiply charged molecules and understand where are these in these systems, what is their transport, what is their fate. And some people even see these showing up in biota when the spills are occurring in surface water. And so cations are actually, those, as I mentioned, disappeared entirely from solution. And so it's not a trivial thing to actually get them back, which is a clue about how tightly they are bound. And it turns out if you're using the standard methods to extract carboxylates and sulfonates from soils and sediments, those do not work on cations, and they're not very good on zwitterions. So a much more aggressive, stronger extraction has been developed by a number of different researchers to try to recover these from soils and sediments. Again, very good clues about the strength of those interactions. And higher ionic strength is simply needed. And so in other words, it's telling us clearly it's not just hydrophobicity anymore. It's understanding and overcoming electrostatic type interactions. And that really brings our attention, and that's where CERTA has focused a lot of funding recently, is on source zones, trying to understand the degree to which cations and zwitterions are still in source zones, making up a significant amount of mass. Again, you're going to pick these up using the top assay, total fluorine kinds of assays. And if you've got a QTOF or a high mass accuracy instrument, you can also see them. EPA in the Midwest was just in Cincinnati yesterday. They've got great instrumentation coming online, and they also have this capability for looking at and finding some of these more exotic PFASs on soils and sediments. Keep in mind, these are all oxidizable. So again, you can pick them up by the top assay, and beware, if you throw oxidants around in the subsurface and you don't know these are there, you can accidentally create a bloom of carboxylates. And so again, that's something you could manage and plan for, but don't get surprised. So that's where, if you've got a site, taking a look at top assay and total fluorine gives you an idea if these kinds of molecules might be present, and you might want to take that into consideration when you're thinking about site characterization and remediation. And the other thing we're thinking about now is this cycling redox conditions, that as these things degrade aerobically to telomere sulfonates, because if you just keep this sulfur atom and you put another OH group on it, you've created telomere sulfonates. They seem to be stable under anaerobic conditions. The minute they go into an oxidative environment, they may take off and again give you a bloom of carboxylates. And so a lot of folks around the world have been looking at oxidation and becoming increasingly aware of the need to close the mass balance. And that's really challenging to do. One, of course, is making sure to look at carboxylates, but then, are gas phase molecules being generated? Are you getting fluoride? Are you doing good QA/QC on your fluoride measurements to show that your oxidation is being efficient? So these are the questions, and this is the pressure for people who are developing remedial techniques, is trying to stack as many tools together to show they understand where the mass is going, and what does that mean for the products if it's not just, say, fluoride being generated. So advanced oxidation, great tool, but it does have that risk of popping up carboxylates, and to some degree, if it's not totally effective, you can also see telomere sulfonate concentrations going up. So that's just a little bit of a note. And so kind of to wrap it up, here's source zones. There's definitely precursors out there. They make up part of that mass. We think that a good fraction of them are strongly interacting through electrostatic type interactions. And for this reason, and if you try to interrogate those soils and sediments using traditional or more conventional extraction methods set up for anions, you're likely to underestimate what's there. So it's a combination of rigorous extraction combined with a more broad scale tool like total oxidizable precursor or total fluorine or QTOF to understand what's in those soils and sediments. And to keep in mind this idea of oxidation, if you want to produce those products, that's great. If you don't, you want to exercise caution when applying oxidants to the subsurface. And we still very much, it's an active research area to understand the role that geochemistry plays in retaining and or liberating these materials from source zone soils and sediments. So to conclude, just a few remarks. PFOS and PFOA are absolutely important. We have health advisory levels, but they are not the only major PFASs at these AFFF sites. We do have a lot of attention currently now focusing towards shorter chain everything, because they tend to be more mobile, and these shorter chain materials have that double whammy in that they're more challenging to remove from water by GAC. That's why people are looking at alternatives like ion exchange and a variety of other kinds of sorbents. And depending on where you look, this missing mass can make up a pretty good, decent chunk of the mass in groundwater. It probably depends. The examples I gave, up to 25%. And it's these species that if you see them or you have indication they're in groundwater, they're mobile. They're potentially on their way to downgradient receptors, and they can be have a whole variety of functionalities on them. That's why they're potentially mobile, cations being the least mobile of them all. And so right now, there's just a whole bunch of research being done on remedial options. Take care when designing those remedial systems and really have a sense for what you're up against during that design stage. And with that, I'd like to thank our sponsors, which is the CERTIP and ESTCP programs. There's a lot of great research going on. I encourage you to look at those websites. It's a really dynamic program, and it's one of the it is the biggest in the country with regard to these substances. And with that, I will thank you very much and apologize for the audio interruption.
Wonderful, wonderful presentation. Back to your comment about recommending Graham Paisley for our seminars. Graham has actually spoken a couple times at our Emerging Contaminants conference that we have in the spring every year. And so I agree, he's a very good presenter, and I'll keep that in mind for him to give a full presentation for our seminar series. And speaking of our conference, if anyone's interested in attending that, the quick link for that is go.illinois.edu/ECEC20, or just Google search Emerging Contaminants Conference at University of Illinois. And then referring to which analytical companies do that top assay test, Charles Neslin from Eurofin says, how about Eurofin? And he will actually be speaking at our conference in spring. So you can hear from industry.
That's my ignorance. Sorry, Chuck.
So before we get into the questions, I'll remind our online audience that you can type in your questions through the GoToWebinar toolbar, and we'll be taking questions from the audience while they're typing in. They're pausing to think as well. Let's see if we have some from our online audience. Yes. What are the general mobility effects from solvent co-contamination?
Ooh, that's a really interesting question. I won't know a whole lot about that, but what I can say is we've been thinking a lot about like why source zone exists, and we've been trying to think back historically how these materials were used. And of course, we know that foam was applied directly to fuels. So let's use fuels as a good example of, say, solvent. And so when we've combined, actually this is the work of Dino Costarellos down at the University of Houston. He's reported that for our project that when he mixes AFFF and fuels together, he gets a gel. And in some ways, it's not entirely surprising because these AFFFs were designed to foam up very much so, block off the oxygen. The other really important functionality was the fuel, the hydrocarbon fuel, doesn't climb the fluorinated lamella of the bubble as well. Like if you put a hydrocarbon surfactant on, they are not effective, which is why we have fluorinated surfactants in these applications. That the hydrocarbons are not that solubilized in the fluorinated surfactant, and so you don't get the reignition. That's why reignitions, you can make these highly restricted mil-spec regulations. So when AFFF in its functioning form came up against fuels, you didn't get good mixing, and so you get emulsions and gels, and that's forcing us to think more differently about what does it mean to have foam in the subsurface. And there's actually good work done on subsurface use of foams for enhanced oil recovery. That's why I pulled Dino onto our project, because he has a background, a very good background in enhanced oil recovery. What works, what doesn't work, because these wouldn't be chosen for enhanced oil recovery. So you kind of have to think backwards, like, so what is it about that when these two things mix? So we are definitely seeing some odd emulsion Windsor type systems. The other thing is we are also working on the partitioning of PFASs into NAPL, and you do get some. And the question is the extent, the partition coefficients, and how does geochemistry impact that? So those are active areas of research.
Okay, another one from online. Are the telomeric compounds also in consumer products or primarily in AFFF?
Well, they're everywhere. So 3M really got busy in the early 60s. And the telomer industry came up not that long after, and it was a way to get around patents and to enter a variety of markets. And so you have essentially competing industry. So the telomer chemistry has actually been around for a long time. And those products and processes are very much out there in commerce. So for example, all the linear PFOA, the Gen X, these were all alternatives to 3M chemistry, the solvate processes. So yeah, there's plenty of different chemistries out in the marketplace today.
Okay, we do have one from our audience here.
Hi, Dr. Field. I have a question. For licensing PFAS, usually, for analysis, we can find some standard or even like isotope standard. But for the if you want a new like a PFOS compound, you cannot find this. You cannot get a commercial available some standard. Even also isotope compound. So I was just wondering how you can quantify them. If you don't, you can identify for the screen, but you cannot quantify them. So how do you quantify this? How do you get this standard? How do you quantify this compound?
Thank you for that question. Well, let's see. I should own stock in Wellington, but I don't. This is the probably the #1 company in the world that carries the greatest number of standards. And they're up, I think our targets are now up to 50 individual standards for which an authentic standard. And then there's a smaller subset of that has an isotope. So we literally buy one of everything that Wellington has for sale. Other companies are also important, like Cambridge Isotopes, and I'm not here to do marketing, but I mean, it's not just Wellington, but there are a number of companies. But you're absolutely right in identifying the fact that there is a limited number of targets. Let's just say that when I got started in this business, which was about 1995, yes, you can do the math, it was a while ago, there was nothing. So you're just looking at an evolutionary step, right? We're in that pathway. So we came from where there were no standards for anything, where we were doing what we call semi-quantitative best estimates, being sure to declare that what you were doing and the assumptions you were making about equimolar response factors. So we have, of our 400 suspects now, we have our 50 targets where we can really button down the quality and articulate that to our collaborators and clients. Those other several hundred compounds, what we have in collaboration with Chris Hagen's lab is a pretty elaborate cross-referencing system where we clearly articulate, here's the compound, here's the structure, here's the closest analog that has a standard, here is the benchmarking isotope. And so it's a set of directions, and it's illuminating our thinking of our best estimates, and we clearly label that as semi-quantitative. And that will evolve with time as more standards become available.
Okay, one from online. What oxidants are used for in situ applications?
That's not really an area, but I mean, you can find lots of literature, Benton's reagent, you can find stuff on, there's potassium permanganate, persulfate, there's everything. Everybody has tried everything, I think with varying degrees of success. The carboxylates are easier to transform, certainly, than the sulfonates.
I did get one pre-question via email, and if I remember correctly, he was asking about there's going to be a large quantity of AFFF that's currently being made, and if everyone switches over to non-PFAS foams, how will those be disposed, and what disposal methods are recommended for that large quantity?
So let me try to understand or maybe rephrase this. So the U.S. military definitely went through a process by which they tried to identify PFOS containing, PFOS containing AFFF. And some of those stockpiles were put through or are being put through incineration. I think that's why you're going to see there was just a piece in CNE News the other day, and Sharon Lerner in The Intercept addressed this question. There's concern about that. So that there was a large-scale effort to take the PFOS-based AFFF out of circulation, which left a lot of the telomers in place. But there is this question about fluorine-free, and there is a movement toward that. Other countries have already done that. Australia, Queensland has done that. They have a fluorine-free foam policy. I think Norway, a number of other European countries have switched to fluorine-free. The question I had for John Cornfield in Brisbane Airport, I'm like, how come you can do that and we can't? And my understanding, it comes down to size. If you're a small country or if you're a small airport, you have a lot of flexibility in terms of purchasing, and you only have so many facilities you have to modify or retrofit. So my understanding is some of these fluorine-frees have different viscosity, and so they don't flow as well. That means your firefighters have to get closer to the fire, so you're having to change firefighting practices, personal protective gear, and training. So you think about the US system, military, think about all those fixed installations, hangars, warships, et cetera, that were built like forever ago. Getting those aging systems switched over, it's difficult apparently to just switch those out because of some of the properties. And also the fluorine-free, because they don't meet mil spec, they don't necessarily blend well. And so what you don't see is the military yet switching over, but they are interested in the question. I have heard that there may be a mil spec for a non-fluorine-free with different specifications, maybe in the offing several years out. And CERTIP is also interested and has begun funding research into fluorine-free, both in the properties, flowability, and firefighting properties, as well as the toxicity. So I think you're seeing things changing. The U.S. military is very large compared to some of these other more nimble systems and countries. And so that's my understanding of why things have changed. I think incineration, we just was a meeting on incineration the other day, trying to understand it, make sure we fully vet it. That's also an active area that people aren't just assuming that, it just works as is under any condition. So it's an active area of research.
Okay, we are coming up to the hour mark. I will ask the last question from online, and then you can leave us with any of your last thoughts. So this last question is high temperature incineration, i.e. 1000 degrees C, still preferred treatment method for treatment of bulk AFFF?
Well, I'm not an expert in it, but I have heard that has been used with some of these stockpiles. What I heard the other day at a sort of EPA meeting was the need to really, really understand that and put, some additional investigations behind that, to further bolster that as a recommendation and to really, really thoroughly understand it. Because a lot of this idea of incineration comes from the literature. It was really pointed toward fluoropolymers, and it's been a little bit dated, and there hasn't been, I think everybody could agree that there has been insufficient investment in that question to really help inform what conditions and for what feedstocks. And there's also, current discussion about trying to get returned energy on that. So that's why it's an area of research. There are still open questions.
Wonderful. Wonderful presentation. I'll be posting the slides and the recording online in the next couple of weeks. Any final thoughts you would like to leave us with?
I assume there's students in the room. You're our future, so follow what you enjoy, and you'll make great contributions. I've had a real pleasure to be able to follow topics that I find interesting, and it took only 25 years for it to become funded, but it's been a real honor and privilege to contribute to the development of this body of knowledge. Thank you.
Thank you.